Do you need to make phase noise measurements, but you're unsure if your reference clock is good enough? Hi, welcome to the lab. My name's Chris Higgins, and today we're going to be looking at the internal reference versions of the 53100A and how that can help you make more accurate phase noise measurements. Traditional phase noise measurements pretty much require that your reference be about 10 dB better in noise than your device under test. This can severely limit your ability to measure high-performance oscillators such as ultra-stable OCXOs or low-noise atomic clocks. This 53100 takes away those limitations, allowing you to measure these high-performance devices with reliability and accuracy. But what does internal reference actually mean? What separates this phase noise test set from the rest? Included in the hardware itself are all the references that you're going to need to measure your devices. Inside are two 100 megahertz OCXOs and a rubidium clock depending on your model. This eliminates the need for any extra cables connecting to infrastructure such as a house atomic reference, and it also allows you to move this device very easily from one station to the next with minimal setup. So there are two different versions of the internal reference model that we offer. One that just has the 200 megahertz OCXOs and one that has a rubidium clock in there for accuracy, and we'll see how that gets differentiated later on. But let's look at the difference in time lab. So here I have two traces of the exact same miniature atomic clock SA55. It's a rubidium clock, it's got great frequency accuracy, but the phase noise plot is about exactly the same. We're going to be getting our phase noise measurements pretty much from the internal OCXOs. That's where you're going to get your low phase noise that you want to measure against. But we'll see the difference when we start to look at our other metrics. So let's switch over to ADEV real quick. And you can see in the blue, we have our trace where we measured against just the IR. This is just against those 100 megahertz OCXOs. And the technology of quartz has things like aging and frequency drift. So this isn't surprising. After about 100 seconds, we start to lose accuracy in our measurement. Now, when we include that rubidium standard, those internal OCXOs are going to be locked to that rubidium frequency. So we'll get about 10 times better frequency measurement. We'll see that in our long-term stability at about 1,000 seconds and even beyond into 4,000 seconds. We're still maintaining accuracy and we're still measuring the absolute limits of our rubidium clock. Let's dig a little more into the internal reference version and some of the options that you can configure inside of TimeLab. So let's go to Acquire, open up the acquisition window. And if you're using an internal reference version, this button will become Ungrade. So let's click on that. And this window that pops up gives you a great overview of the condition of your internal reference model. It tells you if the rubidium's warmed up, if the OCXOs are warmed up, if they're frequency locked together, and what the error between them is. But let's take a look at this calibration setting over here. Let's say it's been a while since you've opened your 53100 and you're unsure if it's completely accurate or not. In this window, you're able to either manually or automatically calibrate your internal reference model. So if you hover over this Auto User Cal button, it actually tells you exactly how to set up your calibration, whether you're using a 10 megahertz signal or you're calibrating it to GNSS using a 1 pulse per second signal. It takes about 5 to 7 minutes to run, but after that, it'll inherit the accuracy of whatever you measured against. Now let's say where you're using this test system has a lot of infrastructure. Let's say a 10 megahertz house signal is running through your lab space. And why would you want an internal reference model? Well, the internal OCXOs also act as cleanup oscillators. So if your 10 megahertz is coming from a cesium clock and the noise floor isn't exactly where you want it to be, you can actually use the internal reference version to clean up that signal to allow you to get to those lower phase noise floor measurements. Let's take a look at that in here real quick. We'll go back to the internal reference menu. And we're able to change the time constant and damping of the external signal that we feed in. So looking at the front right here, if you send your 10 megahertz house signal or cesium frequency standard or whatever your house standard is into this, you can still use the internal OCXOs that are built in. That was our quick look at the internal reference models of the 53100. If you want to know more about these models in particular, we have an application note that goes in depth into these references and how they can improve your measurements. As always, if you want to know more about the system as a whole, we have plenty of links in the description for you to check out. Thanks, and I'll see you in the lab again soon.